I have actually given a question to you in the screen. All of you have tried it. Do you have any answer for the question? Any of you have got the answer for this particular question? Yeah, Manchunad, e to the power j theta plus or minus j theta is the correct answer. You got the correct answer. But we'll discuss this later. Before that, this problem is kept for today's discussion. We'll see different implications of this rotating matrix. I'll continue with last class. In the last class, we have listed the properties of eigenvalues. If you recollect it, I'll just go through it quickly. First property was, okay, 1 second. Okay, first property was the trace is equal to sum of eigenvalues. Trace is equal to sum of eigenvalues. Okay. Then second property was determinant is equal to product of eigenvalues, right? Then third property was if A is having an eigenvalues lambda 1, lambda 2, etc., lambda n, then A raised to n will have eigenvalues lambda 1 raised to n, lambda 2 raised to n, etc., lambda n raised to n, and it's applicable with all positive and negative integer values of n, right? Then k times A will have eigenvalues k times lambda 1, k times lambda 2, etc., k times lambda n. Then A plus k times I will have eigenvalues lambda 1 plus k, lambda 2 plus k, etc., lambda n plus k. I think all these properties were detailed in the last class. We have taken an example problem and have seen what it means. Now I'll list out another important property of a matrix, eigenvalues. If all rows add up to a same number, add up to a single number, if all rows add up to a single number, then that number will be an eigenvalue. That number will be an eigenvalue. Will be an eigenvalue. Okay, this was a property. I don't think this was listed in the previous class. So if all rows add up to a single number, then that number will be an eigenvalue. Let us just check whether that is correct or not. So our symmetric matrix was 3, 1, 1, 3. So what I told is if all rows add up to a same number, here all rows, 2 rows are there, all rows are adding up to the number 4, which means 4 will be an eigenvalue of this matrix. And if you are applying this particular property, then the corresponding eigenvector will be nothing but 1, 1. That is also known to us. So if I multiply this matrix by 1, 1, the result will be 4, 4, correct? 3 into 1 plus 1 into 1. So that is equal to 4 times 1, 1, which means I have 4. See, the vector is remaining the same. I have 4 as the eigenvalue. Now, in GATE 2017, one problem was asked in EC branch. It was regarding a 5 by 5 matrix. 1, 2, 3, 4, 5. 5, 1, 2, 3, 4. 4, 5, 1, 2, 3. 3, 4, 5, 1, 2. 2, 3, 4, 5, 1. This was the matrix given, 5 by 5 matrix. And they have asked the question, only one real eigenvalue is there for this particular question, this particular matrix, and what is that eigenvalue? And I think we have discussed this question in the last class. We have seen the eigenvector to be the same eigenvector. And since all rows are adding up to the same number, that number will be an eigenvalue. You can just calculate it. You will get it as 15, 15, 15, 15, and 15, which means that is, I can take out that 15 out. So it will be like this, right? See, this vector and this vector are same. So this is naturally, see, you should observe it as A times X is equal to lambda times X. So lambda is 15, right? So lambda is 15, and that is the correct answer for this particular question. Now we'll see some other properties of eigen. We have not discussed how to evaluate the eigenvector of a matrix. Actually, I have taken this eigenvector and another eigenvector 1, minus 1 directly from this matrix, which is actually known to me. I have not described how the normal procedure is there, normal procedure is to evaluate this vector. So we'll see how to evaluate the eigenvector of this particular matrix or any particular matrix. This is the common method. Okay. So in evaluating eigenvalues, I take A minus lambda I matrix into x vector is equal to 0. This is the equation I start off with, correct? And I then applying homogeneous equations property for this to have any solution other than x is equal to 0, we need to have determinant of A minus lambda equal to 0. For non-trivial solutions, our requirement is determinant of A minus lambda I equal to 0. This gives you the characteristic equation of the matrix, and that characteristic equation will be a polynomial equal to 0. If you solve for the polynomial, you get different eigenvalues, correct? So that is how we evaluated eigenvalues. Now let us see how we can evaluate eigenvectors of this particular matrix. Let us take the matrix, this matrix itself. I have 3 1 1 3, and in the last class we have done the analysis for this matrix in eigenvalues. So we got eigenvalues as 4 and 2. Okay, so and one more property I have listed was for distinct eigenvalues there will be linearly independent eigenvectors. So I have these values are distinct, lambda 1 and lambda 2 are different values, right? They are not same values, which means I'll have one eigenvector corresponding to lambda 1 and another eigenvector corresponding to lambda 2. Both will be linearly independent, correct? So how do you evaluate the eigenvector corresponding to lambda 1 equal to 4? I'll do first this operation. I take A minus lambda times I is lambda here 0 0 lambda, correct? Lambda into identity matrix, that is this part, first part, right? And now the second matrix is C. In choosing the eigenvector, I am assuming a vector which is having the same dimension as that of the square matrix. Our square matrix is of 2 by 2. So I can choose the dimension of this column vector as 2. So I am choosing h1, h2 equal to 0. Correct. Now what it means? It means I'll have 3 minus lambda. I am choosing, I want to find out eigenvector corresponding to this lambda 1, which means I need to put lambda 1 equal to 4. So if I put that 4, 3 minus 4, correct? 3 minus lambda 1 is 4, 1 minus 0, that is 1, 1 minus 0, that is 1, 3 minus lambda 1, again 3 minus 4, correct? Into, now h1, h2, right? That is equal to, my column is 0, 0, resultant is 0, 0. So what it means, this will give minus 1, 1, 1 minus 1 into h1, h2 into h1, h2 equal to 0. Now, once you have this equation, you can easily see that the rank of this particular matrix is 1. Because if the first row, I consider the first row into minus 1 is second row, correct? So that is a weighted sum of the weighted value of first row, which means only one row carries any information. Only one row carries any information, and that particular row I have taken as first row. So second row is actually a replica, correct? So I need not bother about the second row. I have information only in the first row. So I'll multiply this first row with first column. I'll write minus 1 into h1, correct? Plus 1 into h2 plus 1 into h2 equal to 0. Now, if you write the second row into first, column, that will give the same equation multiplied by minus 1, which is of no use to us because it is not giving us any additional information, right? So now I have from this particular equation, I will assume one value for h1, which is k. I am assuming the value of h1 equal to k, which means I have minus k plus h2 equal to 0, correct? So what is h2 then? h2 is also equal to k. So if I take same values k, then that is obeying this particular equation. That is the meaning, correct? If I take k, that is obeying this particular equation for this particular eigenvalue. Let us see what is going to happen. If I take 3 1 1 3 times k, what is going to be the result? 3k plus k is 4k, and 1k plus 3k, that is again 4k. So I can take out 4 and write kk, correct? Now, so kk is particularly giving you actually a direction. right? Kk is giving you a direction which is equally inclined to both x-axis and y-axis. I can take any point on this line and that will be an eigenvector. I can take any point on this line and that will be an eigenvector corresponding to the eigenvalue 4. If I put 1, 1, that is the case which we have seen. If I put 1, 1, I'll have 4, 4, right? If I put 2, 2 point, then that will give me 8, 8. Again, the eigenvector is multiplied by 4 times. So any vector lying on this line, in this line, see if I take 3, 1, 1, 3 times minus 2, minus 2, that is also obeying this condition, correct? So that is minus 6, minus 2, minus 8, minus 2, minus 6, that is minus 8. So that is again minus 8 times, sorry, minus 4 times, sorry, 4 times, 4 times minus 2, minus 2, correct? That is minus 8, minus 8. Which means my eigenvector is this particular direction, having this particular direction, correct? So that is why in general you can take 1, 1 as an eigenvector, 2, 2 is an eigenvector, but they are all lying on the same line, which means they are linearly dependent. Any eigenvector written in the form kk, you can choose 1, 1 as an eigenvector, you can choose 2, 2 as an eigenvector, you can choose 3, 3 as an eigenvector. All these are eigenvectors, but they are all lying on the same line, which means they are dependent. That is what is meant by you will have, I told you, you will have two linearly independent eigenvectors corresponding to lambda 1 equal to 4 and lambda 1 2 equal to 2. For lambda 1 equal to 4, I got one set of eigenvectors. For lambda 2 equal to 2, I'll have another set of eigenvectors which is linearly independent with this vector. Okay, so I'll now try to find out the eigenvector corresponding to 2. Let us see what will be the eigenvector corresponding to 2. So now you can easily write 3 minus 2, correct? That is what is a minus lambda I. 3 minus 2, 1, 1, 3 minus 2 times h1, h2 equal to 0, 0, right? 3 minus 2 is 1. So 1 times 1, 1, 1, 1 will be this particular matrix. Again, you can see only one row carries information. The second row is just a replica of the first row, correct? Into h1, h2 equal to 0, 0, correct? So what does that imply? That implies h1 plus h2 equal to 0. Now, applying the same principle as I have seen before, I am applying, I am putting k h1 equal to k. If I put h1 equal to k, naturally h2 is equal to minus k, because h1 if I take to the right side, that becomes minus. So what is the eigenvector? The eigenvector is k minus k. Now you can apply give any integer value. So if I put k equal to 1, that will be 1 minus 1. 1 minus 1 is an eigenvector corresponding to the eigenvalue lambda 2 equal to 2, and 1, 1 is an eigenvector corresponding to the eigenvalue lambda 1 equal to 4. And since these eigenvalues are distinct, our property is obeyed. What is our property? Our property is, if there are n distinct eigenvalues for a particular matrix, then there will be n linearly independent eigenvectors. You can see these two eigenvectors are linearly independent. Okay, what can you say anything additional about these two eigenvectors? Seeing these columns, can you say something additional? They are linearly independent. See, if I have 1, 1 and 1, 2, these are also linearly independent, correct? 1, 1 and 1, 3, they are also linearly independent. But 1, 1 and 1 minus 1 have an additional property. What is that? Can someone tell me? Yeah, orthogonal. Abhiram, very right, very good. Because they are orthogonal. Orthogonal means dot product will be 0. 1 into 1 plus 1 into minus 1 equal to 0. So that is a property corresponding to this particular matrix which I have chosen. Which is the matrix which I have chosen? This is a matrix 3, 1, 1, 3. So that property I list down. That is a very important property. For a symmetric matrix, you must remember we have taken the example 3, 1, 1, 3, which is a symmetric matrix. For a symmetric matrix, eigenvectors will be orthogonal. For a symmetric matrix, eigenvectors will be orthogonal. So that is an important property. Yes, Shehin, Sujit, all of you are right. They are orthogonal. So this is a particular property of an symmetric matrix, which you should note down. Please note down this particular property. For a symmetric matrix, eigenvectors will be orthogonal. So I hope the idea of how to evaluate the eigenvector is clear to you. Should I need to repeat the process, or should I give you the slide to write it down? Anybody, if you want, you can chat or unmute and tell me. If you have any doubts, you can ask. If you have any doubts, you can ask. No, no, I hope it is okay. Do you want time to write it down? If you respond only, I can understand something. Orthogonal is correct. No, no need to write it down. Okay, so we'll move on. Right. Now we'll come back to the particular problem which you have started off with. So the question was cos theta minus sine theta and sine theta cos theta. Okay, so you know what this matrix does. In the linear transformation class, I have given you example of vector operated by this matrix, and we have seen if you give a 1 1 vector, naturally that will be rotated by an angle of theta counterclockwise. So there is a puzzle here. What is a puzzle? Eigenvector idea is clear. Okay, eigenvector idea is you need to have some vector h1 h2, right, which will keep its direction. It should, if you operate with this matrix, I should get lambda times h1 and lambda times h2, then only I can say this is an eigenvector. But how is that possible? Because this will always rotate any vector, correct? This will always rotate any vector, which means what does that give you? What information will it give you regarding the eigenvector? We'll see what it reveals. Okay, we'll first evaluate what is the eigenvalue of this particular matrix. For the eigenvalue, it can be evaluated as determinant of a minus lambda I equal to 0. How many of you got the answer as e to the power plus or minus I theta? Can someone, I know Manjunath Vishnumurthy has got the answer. Anybody else got the answer for this particular problem as e to the power minus I theta, minus or plus I theta? No, no others got the answer. Okay. See, we'll see what or how cos theta plus I sin theta. That is correct. Cos theta plus I sin theta is nothing but e to the right theta only. Okay. So I'll take cos theta minus lambda. Correct. I need to subtract diagonal lambda from diagonal elements, minus sin theta, then sin theta and cos theta minus lambda. Correct. So that is determinant a minus lambda I, that is equal to 0 means I need to multiply the diagonal elements, cos theta minus lambda the whole square minus sin theta into minus sin theta is minus sin square theta. So this becomes plus sin square theta equal to 0. I'll explain this term lambda square minus 2 lambda cos theta plus cos square theta plus sin square theta equal to 0. I know cos square theta plus sin square theta is 1. So you have the equation now, lambda square minus 2 lambda cos theta plus 1 equal to 0. Lambda square minus 2 lambda cos theta plus 1 equal to 0. You can solve it using the quadratic equation formula. Lambda is here, you need to assume lambda is h. So h square minus 2h cos theta plus 1 equal to 0, which means lambda will be equal to minus b. What is the coefficient of lambda here? Minus 2 theta, minus 2 cos theta. So that will be minus b will be 2 cos theta plus or minus root of b square. B square is 4 cos square theta minus 4 AC, 4 into 1 into 1. So 4 whole divided by 2, correct? So that is equal to 2 cos theta plus or minus root of, I can take minus 4 from here. Minus 4 if I take, that will be 1 minus cos square theta, correct? Whole divided by 2. So that is equal to minus 2 cos theta plus or minus square root of minus 4 is 2i, correct? I into 2 into 1 minus cos square theta is nothing but sin square theta. So if I take the square root, that will be sin theta, correct? Whole divided by 2. I can cancel out 2. Sorry, minus is not here, plus only. Minus is not here. So plus 2. So what is the answer? The answer is cos theta plus or minus I sin theta. That is the answer. So the eigenvalues are lambda 1 equal to cos theta plus I sin theta and lambda 2 equal to cos theta minus I sin theta. These are the two eigenvalues, right? These are the two eigenvalues. Correct. So I can write this is equal to e to the power I theta and this is equal to e to the power minus I theta. These are the two eigenvalues for this particular matrix. Which matrix? Cos theta minus sin theta and sin theta and cos theta. This is a matrix, right? I have this particular two eigenvalues. Correct. Now that means that gives you a very important idea. You know, this particular matrix is going to rotate any vector by an angle of theta. So what if theta equal to 0? If theta equal to 0, this matrix becomes cos 0 is 1, 0, 0, 1, which means identity matrix. Which means, see, if you take identity matrix, any vector is an eigenvector. That is the only case when this is equal to 1. When theta equal to 0, this is 1 and I sin theta term becomes 0. So that will be 1. This will also be 1. That is when theta equal to 0. That is a special case. That is, it will not rotate by an angle theta. It will actually keep the direction. That is when theta equal to 0. Now what if theta equal to 180 degree? If theta equal to 180 degree, you have cos theta equal to minus 1, sin theta again 0, sin theta again 0, cos theta equal to minus 1. So this case, this is actually having an eigenvalues. See, if it's a diagonal matrix, all diagonal elements will be the eigenvalues. For a diagonal matrix, all diagonal elements will be the eigenvalues. So the eigenvalues for this particular matrix are minus 1, 0 and sorry, minus 1 and minus 1. Which means if you multiply this matrix with any vector, okay, you have 3, 2. What will be the result? The result will be minus 3, minus 2 because the eigenvalue is going to be minus 1. So those are the special cases for this particular matrix with theta equal to 0 and theta equal to 180 degree. What is actually happening? What is actually happening is when theta equal to 0, the resultant vector will lie on the same vector. When theta equal to minus 1, the resultant vector lies on the line, but it will get reflected. That reflection is indicated by the negative sign. The reflection is indicated by the negative sign. Still, we cannot say it is not an eigenvector because they are lying on the same line. So an eigenvector with minus n. Now, can you think of any other value for theta where there is a real eigenvalue? No, because for any other theta, this matrix will actually rotate the vector by an angle other than 0 or 180 degree. If it is rotating a vector by an angle other than 0 or 180 degree, it implies it is losing its direction. Correct? So the basic idea of eigenvector is it should not lose its direction, which means I cannot have any other real vectors which are eigenvectors of this particular matrix for theta not equal to 0, not equal to 180 degree. For theta not equal to 0, not equal to 180 degree, you cannot have a real eigenvector for this matrix because any of the vector is going to rotate. If it rotates, it loses its direction. Is the idea clear to you? Now I'll give a homework for you. You just need to evaluate the eigenvector corresponding to e raised to I theta, and you need to evaluate the eigenvector corresponding to e raised to minus I theta. Please note it down as a homework. You can get answers for that, but the answer will actually be imaginary because we know there will not be any real vectors. Okay, so you just try working out this problem to evaluate the eigenvector corresponding to these two eigenvalues. So is the idea clear to you? Shall we proceed? If the idea is clear to you, I can proceed. Anybody have any doubts? Clear, Shahin, it's clear. Shall I give one question to you? Clear. Okay. Shiv Prasad, it's clear to you. Anybody has got any doubt? Okay. This question clear. Okay. This question. This is one question you can take down. Find the value of P such that the value of P such that the vector 1, 2, 3 is an eigenvector of the matrix 4, 1, 2, P 2, 1, 14 minus 4, 10. So the question is dash. You need to find out the value of the matrix, I mean the value of P in this particular matrix, so that this vector becomes an eigenvector. You are not given any other information. You are given the matrix, but one value is not given to you. And this question was asked in GATE 2014 EC paper. Okay. You are asked to find out the value of P so that this particular vector will be an eigenvector of this matrix. You can try. I'll give you 2 minutes. You can try. Yeah. Manjuna, your answer is correct. Somebody might be trying, so I'm not reading it out loud. Let others, if they get, that is good. Sujit, you are also correct. Okay. Arvind, right? Correct. So most of you are having clear-cut idea about eigenvectors, I think now, because that's a conceptual question. Once you have the idea of the eigenvector concept, you can easily solve it. Arvind Ramakrishnan, you are correct. Okay, I'll solve it because we Ashwadi, you got it correct. Okay, I'll solve it because we don't have too much time to wait. We are only having 1.5 sessions. Okay, so this is pretty simple. Once you have given eigenvector, it must obey Ax equal to lambda x. We don't know the value of lambda, but that's okay. But we have most of the values of A, and all the values of x are given to you. So this side is also almost given to you. So what happens if I multiply this particular matrix 1, 4, 2, P 2, 1 and 14 minus 4, 10 with this particular vector? That is my first knowledge, correct? This is the only thing I know. So I'm going to multiply 4 into 1, 4, 4 plus 2, 2, 2 plus 4 plus 2, 6, 6 plus 6, 12 will be the first value. P into 1, P plus 4 plus 3. So this will be P plus 7, right? Next will be 14 minus 8, 6 plus 30. So 36. Now I am going to compare this vector and this vector. It should be this vector multiplied by some vector should give me this vector. So if I compare 1 and 12, 1 into 12 is 12. 2 into 12 is, if it is P plus 7, my idea is correct. 3 into 12 is 36. Correct? Correct. So what should be the value of P? P is equal to 2 into 12 minus 7, which is 17. So if I put P equal to 17, 17 plus 7, 24. So I'll get the vector 12, 24, 36, which is equal to 12 times 1, 2, 3. So the eigenvalue is 12. Correct? The eigenvalue is 12 and the value of P should be 17 is the correct answer. Right? Okay, shall I proceed? Is it clear to all of you? It's a direct problem. Sir, I went out with the last question. Is there any relevance for the axis of rotation? Yeah, the axis of rotation is relevant, but for this two-dimensional case, that is not relevant. For three-dimensional case, we'll see rotation matrices where the rotation will be based on some particular axis, right? For this particular case, we are just rotating the matrix in 2D plane. So the rotation axis is not relevant, but for some other matrices in 3 dimension, rotation axis becomes relevant when we see the eigenvalues and eigenvectors. For this particular case, it's not making any change because there is only 2 eigenvalues which are going to be real. One is 1 and the other is -1. 1 happens when theta equal to 0, -1 happens when theta equal to 180 degree. Any other doubts? If no doubts, I can proceed. Right. So I am proceeding. Now we will see some special matrices where the eigenvalues are peculiar. So we just need to learn first the matrices. I'll take the case of real matrices first. The real means all the elements are real. So the first matrix I take is A transpose equal to A case, and that is called as symmetric matrix. Okay, that is called as symmetric matrix. Now the second matrix I take is A transpose equal to minus A, and that is called as, we have learned it. What is called, that is called as skew symmetric matrix. Skew symmetric matrix. And the third one I take A transpose equal to A inverse. That is called as orthogonal matrix, correct? Orthogonal matrix. Now this is the first class. For complex entries, complex matrices, you just need to remember one thing. In complex matrices, the term transposition means actually transposing as well as taking complex conjugate. That is it. Okay. Transpose in complex matrices is not just A transpose, but it is actually A transpose conjugate. So I'll write for complex matrices. The first matrix is A transpose. Instead of just transpose, I need to write conjugate. Conjugate means you need to take the complex conjugate of each and every entry in the matrix. I'll give an example. Suppose 1 plus I, 1 minus I, 2I, and 3I. What is the conjugate of this matrix? The conjugate is 1 minus I, 1 plus I, minus 2I, and minus 3I. Now the transpose is 1 minus I, minus 2I, 1 plus I, minus 3I. So this matrix conjugate and then transpose means it will be, resultant will be this one. So you need to interchange rows to columns, columns to rows, and then take conjugate of each and every element. That is what is meant by A transpose whole conjugate. Correct? So A transpose whole conjugate equal to A. We call that matrix, it's in the class of symmetric, but we call this special matrix as Hermitian matrix. Okay. So the second will be A transpose whole conjugate equal to minus A. What it will be called? You can guess. It will be skew Hermitian. Skew Hermitian matrix. Skew Hermitian matrix. And the third one is A transpose whole conjugate equal to A inverse. And the corresponding one in real is orthogonal, but here we call the name unitary matrix. Unitary matrix. Now, these three are very important matrices because their eigenvalues will always follow a special pattern. That is why it is very important. So to remember the pattern of eigenvalues, I'll just draw the 2-dimensional space in with real as well as imaginary axis, and we'll see how we can remember that particular pattern. Okay. So first we'll draw the 2-dimensional plane. Now this is real axis. Okay, this is real axis, and this is imaginary axis. Okay, this is real axis and this is imaginary axis. Now the first element from real and complex, that is symmetric and Hermitian matrices. For these two matrices, the eigenvalues will always lie on real axis, which means whenever you see a symmetric matrix or Hermitian matrix, you can be pretty sure that the eigenvalues are going to be lying on the real axis, which means there will be purely real numbers. There will not be any imaginary part. There will not be any imaginary part for the first class of real and complex matrices. One is symmetric, another is Hermitian. For both these cases, eigenvalues will lie on real axis. Now the second cases are skew symmetric and skew Hermitian. Skew symmetric and skew Hermitian matrices, the eigenvalues will lie on imaginary axis. Okay, which means for skew symmetric matrix and skew Hermitian matrix, my eigenvalues will always lie on imaginary axis. Now that gives you one more information. There will be one real value in the imaginary axis. Which is our real value? Can someone say in chat? Directly. 0. Correct. 0 is a part of imaginary axis as well. So 0 is also possibility of skew symmetric and skew Hermitian matrices eigenvalues. Correct. So if you there was one question in a gate paper, I think it was in 2010 or 2010 EC paper. You can check that paper. The question was, for all skew symmetric matrices, the eigenvalues will be. They have given 4 options. One option was always imaginary, always real, generally complex, and the last option was either purely imaginary or 0. Okay, so the correct answer for that particular question is either purely imaginary or 0, and that is applicable for skew symmetric as well as skew Hermitian matrices. For skew symmetric and skew Hermitian, the proof of these things are irrelevant to you. You just need to learn the information. We can easily prove it. If you want, I can prove the case for symmetric. The other things you can work out from home. Okay, so the idea is it will always lie on the imaginary axis, which means the eigenvalues are going to be either purely imaginary or 0. Either purely imaginary or 0. So that is the possibility for second class, which is skew symmetric and skew Hermitian matrices. Now the third class, which is a very important class, orthogonal matrices and unitary matrices. Okay, for orthogonal matrices and unitary matrices, the eigenvalues will actually lie on a unit circle. What is meant by unit circle? I will tell you. Unit circle. So this is the case with eigenvalues for the last case, which is orthogonal as well as symmetric matrices. I mean unitary matrices. What is meant by unit circle? Unit circle means if you take any complex number in the plane, let us say a plus ib is a complex number. What is the magnitude of this complex number? It will be root of a square plus b square. That is actually giving you the distance from the origin. Suppose I take this particular point. The a component will be here and the b component will be here, right? So the magnitude of that will be the hypotenuse. That is actually the distance of that particular point from origin. That magnitude will be 1. I'll give an example. I take the value 1 by 2 plus I root 3 by 2. What is going to be the magnitude of this particular vector? That will be root of 1 by 2 whole square is 1 by 4 plus root 3 by 2 whole square is 3 by 4. So its magnitude is going to be 1. Correct? So that is lying on one point is 1 by 2 plus I root 3 by 2. You can see another points. This point will be 1, 0. What will be this point? This point will be 0, I. Correct? 0 in the real axis, I in the magnitude of I is 1. This point will be minus 1, 0. This point will be 0, minus I. Correct? So all these points lie on a unit circle. Whenever you see an orthogonal matrix or a unitary matrix, all the eigenvalues are always going to lie on the unit circle, which means the magnitude of the eigenvalue will always be 1. The magnitude of the eigenvalue will be always be 1. So I am stopping here for a break. So this slide I am keeping as such. It will be very nice if you can copy down this slide exactly in the same format so that you can remember it easily. Okay. After the break, I'll come back after 5 minutes. So if you have any doubts, you can put it in the chat window. No. All of you are clear about this slide? Everything is clear? Am I audible? Yes, clear. So shall I proceed? I'll take an example of the from GATE question paper to clear the doubt asked by Anumol. Okay. Okay, you can take down this question. Find the value of x. The value of x for which value of h for which all the eigenvalues of the matrix given below are real. The matrix is 10, 5 plus j, 4, x, 20, 2, 4, 2, minus 10. So this is the question. And the question is directly from the concept which we have seen in the last slide. This is a direct question from the concept which we have seen in the last slide. I'll give you 1 minute to solve this. What should be the value of h is the question. There are 4 options given to you. I'll list out the options. First option is 5 plus j. Second option is 5 minus j. And third option is 1 minus 5j. And last option is 1 plus 5j. Which one will give you the answer? Question is value of h for which all the eigenvalues of the matrix are real. And it's a question which was asked in GATE 2015 EC paper. All of you are getting the answer is 5 plus j. Atira has got the answer 5 minus j. Manjunath has got the answer 5 minus j. Option B is given by Lakshmi. 5 minus j. So different answers are coming up. That's nice. 5 minus j. So 5 minus j. 5 minus j. I'm very happy because Anumol, you made the mistake again. Achana. Okay. Bhavya. Great. It's great to see all of you answering. Most of you, 90% are answering correctly. 5 minus j is the correct answer. Shilpa, you're also right. I'm not reading out all the names. So many have answered correctly. So let us see what is the fundamental principle. The eigenvalues of the matrix given below should be real, right? So where all we have seen real eigenvalues if A transpose equal to A or A transpose whole conjugate equal to A. These two belong to two different class of matrices. This can be applied only if all the elements of the matrix are real. This can be applied if the elements of the matrix includes complex numbers. So we have seen in the matrix there is a complex value, which means this matrix is not the one which you should look for. I can only check for now this particular matrix which is coming under the class of Hermitian matrices. For Hermitian matrices, eigenvalues are real, right? Which means I need to take the transpose as well as conjugate. How do you take the transpose of this particular matrix? 10, x, 4, 20, 10 x 4, 5 plus j. Next value will be 5 plus j, 22. Now 4, 2, minus 10. Right now, how do you get the? This is just a transpose. This is A. Now this is A transpose. We need to get the conjugate also, right? A transpose whole conjugate means I need to get the conjugate of each and every number. So conjugate of each and every number means 10, 4, 22, 4, 2, minus 10. All these are real numbers. So even if you take the conjugate of real numbers, they are going to remain the same. X, I don't know whether it is a real or complex number. So I'll just write X conjugate. Right? The real numbers I'll write the same. 5 plus j, if I take the conjugate, it will be 5 minus j. Correct? 20 remains the same. 2 remains the same. 4, 2, minus 10. Now, this is A transpose whole conjugate. Now, my requirement is A transpose whole conjugate must be equal to A, which means this matrix must be equal to this matrix. Correct? So, X conjugate should be equal to 5 plus j, or X should be equal to 5 minus j. Correct? H should be equal to 5 minus j. Now, is it clear for you, Anamol, how to take the conjugate? Conjugate is nothing but we should take the complex conjugate of each and every number. Okay. Right. Thank you. So we shall proceed to the next point. Now, I have something more to tell you regarding the characteristic equation, which I should not miss because normally there will be gate question from that particular part, which is called as Cayley-Hamilton theorem. Cayley, it is Cayley, Hamilton theorem. It says if you get the characteristic equation of a matrix in terms of the eigenvalues, you can always replace eigenvalues by the matrix itself and any constants by constant times identity matrix in the equation, and still the equation will be valued. Okay, that is, if you get the characteristic equation of any matrix from this particular relation, determinants of a minus lambda. For example, I'm taking our matrix which we normally use. This is the matrix which we took for example. For this particular matrix, determinants of a minus lambda was lambda square minus I think it was 6 lambda plus 8 equal to 0, correct? Then only lambda minus 4 into lambda minus 2 gives me 0. So product is 8 and sum is 6, right? So this is a characteristic equation of this particular matrix. Now the theorem says you can replace lambda by the matrix itself. If I name the matrix as A, the theorem says you can replace the lambda by the matrix and any constant by constant times identity matrix. So lambda replaced by A means I have A square minus 6 times A plus constant will be replaced by constant times identity matrix, that is equal to 0. This is what is Cayley-Hamilton theorem says, which means what is the requirement of this particular theorem? See, I can calculate now A square as A square is equal to 6A minus 8I. Okay, so that is just scaling a matrix and doing some subtraction instead of doing to matrix multiplication, correct? From this equation I can write A square equal to 6A minus 8I. More importantly, if I have this from this relation 1, I can take 6A equal to A square plus 8I, correct? Right? So if I multiply this both equations by A inverse, 6 times A into A inverse equal to A square into A inverse plus 8 into A inverse, correct? Because I am multiplying both sides by A inverse. A into A inverse is I, so I write A 6I equal to A square into A inverse is A plus 8 times A inverse, correct? So I can write A inverse is equal to 6I minus A whole divided by 8, correct? So that is a very interesting result because I can evaluate the inverse of a matrix simply by doing some scaling of identity matrix, subtraction by the original matrix, and scaling by a constant. You don't need to bother about the adjoint of a matrix, determinant of a matrix, etc. to evaluate A inverse, correct? Also, one more important property I can tell you. See, if you want to evaluate A raised to 8, I can take A square. A raised to 4 will be 6A minus 8I whole square. Again, recursively, I can change A square into this value. So ideally, A to the power n can be effectively written in terms of some constant times A plus another constant times I. That'll give you the calculations much simpler, right? An opportunity to do the matrix power using scaling of a matrix and scaling of identity matrix and addition. That is the important of this particular idea. Okay, that is important of this particular idea. So we'll see some problems based on this. So you should note it down. Cayley-Hamilton theorem says we can in the characteristic equation. I'll write the note in the characteristic equation. In the characteristic equation of a matrix, lambda can be replaced by matrix, and okay, and any constant can be replaced by constant times identity matrix, and any constant can be replaced by constant into constant times I. I represents identity matrix of the same order. I represents identity matrix of the same order. Okay, is it clear? Is it clear? I'll give another. Shall I change the slide? Do you want to write it down? Do you want more time? Can I change? If you are writing, please. I'm waiting. Otherwise, you can type please yes, so that I can change the slide. Okay. Right. Okay. I'm changing the slide. I'll give another question. The matrix. This is another question. The matrix 5, 10, 10, 1, 0, 2, 3, 6, 6 has got only one real eigenvalue. Has got only one real eigenvalue. The real eigenvalue is dash. That is the question. This was also asked. I don't recollect the year of the gate paper, but you can try this. You can try answering this particular problem. What is the answer? Yeah, most of you you're getting 11 as the eigenvalue. How do you get 11? 11 is an eigenvalue. Vardhan. How are you getting the answer as 11? Shehin, Manjunath, Shruti, you're correct. 0 is the correct answer. I don't know how you're getting an answer of 7. Something which you might have applied which is wrong. Sum of trace is 11. That is correct. Sum of trace is correct. That means the trace, sum of diagonal elements is trace, but that is not an eigenvalue. Determinant equal to 0. Correct? Yes, determinant is 0. So Richard, you made a mistake. I'll tell you why. What is the mistake? Actually, trace is 7. Trace is 11. That is correct. Trace of the matrix is 11. Trace is equal to 11. Does that mean that trace is an eigenvalue? No. Trace is actually, if you have 3 eigenvalues, I can say lambda 1 plus lambda 2 plus lambda 3 equal to 11. That is the only information which you get from this particular matrix. Correct? So you cannot say any of these eigenvalues 11. The real eigenvalue, what is the real eigenvalue? That is the question. Now, determinant will be 0, which you can directly say from this matrix, because the row 1 is actually 5, 10, 10. So if I take row 1 by 5, that is nothing but that is 1, 2, 2. Row 1 if I divide by 5, that is 1, 2, 2. And row 2 if I divide by 3, sorry, row 3. Row 3 if I, row 3 and row 1. Okay. Row 1 if I divide by 5, that is 1, 2, 2. Row 3 if I divide by 3, that is again 1, 2, 2. Which means 2 rows are linearly dependent, because I can say row 1 is equal to 5 by 3 times row 3. Correct? Just by looking into these rows, you can say this determinant is going to be 0. If the determinant of any matrix is 0, then 0 is going to be an eigenvalue. 0 will be an eigenvalue. Okay? And another thing is 0 is a real number. 0 is a real number. And in the particular question, they have given that the matrix has got only one real eigenvalue. And I am sure that 0 is an eigenvalue. So that real eigenvalue must be 0. Now you can say, you can argue me whether other real eigenvalues, other values gives an number of 11. That is possible. If suppose I have lambda 3 equal to 0, I take lambda 2 equal to 5.5 plus 3j, lambda 2 equal to 5.5 minus 3j. If I add up these two numbers, this is a complex eigenvalue, this is a complex eigenvalue, and 0 is the other eigenvalue. If I add up all these three numbers, minus 3j and plus 3j will cancel out. 5.5 plus 5.5 will give me 11, plus 0, 11. So trace is satisfied, correct? So trace is satisfied. 0 is an eigenvalue. So you cannot take trace as an eigenvalue. Did you understand the mistake, Richard? Okay. So this, for this particular problem, 0 is the correct answer. 0 is the correct answer, right? So looking into the question itself, you can answer it as 0. Right. So if all of you are clear about it, I can proceed. Now I have told you the symmetric matrix will have eigenvalues given by for a symmetric matrix, eigenvectors will be orthogonal, right? So we have another interesting result which should be derived. This is called as diagonalization of a matrix. So I'll just go through diagonalization as well. Diagonalization. This is very important because this part you can apply in your engineering subjects. In many of the subjects, this diagonalization will be applied to get into some important core concepts of the subject. Okay, so this is very important. A bit hard to understand the concept, but we'll first we'll list out the mathematical part of this diagonalization. In the next class, I'll reveal the engineering side of diagonalization. Okay, so first you should understand the procedure of the diagonalization. In the next class, initially we'll see the engineering side of diagonalization. Okay, or engineering applications of diagonalization of a matrix. So I have a matrix A. Okay, which I am taking the easiest matrix to solve, which is 3 1 1 3. This is the matrix which I have solved. I know the eigenvalues of this particular matrix are 4 and 2, and the eigenvectors corresponding to this matrix are 1 1 and 1 minus 1. Okay, 1 1 and 1 minus 1 are the eigenvectors, and 4 2 are the eigenvalues. Okay, now I am creating another matrix called as S using these eigenvectors. The two eigenvectors which I have are 1 1 and 1 minus 1. These two are the eigenvectors of this particular matrix, right? Now this diagonalization procedure is applicable for only those matrices where the eigenvectors are going to be linearly independent. Okay, diagonalization is possible only if eigenvectors are linearly independent. Eigenvectors are linearly independent. This is an important point. You must remember that for any matrix, if you want to diagonalize the matrix, then you must have eigenvectors which are linearly independent. Then only you can do the diagonalization procedure. Okay, so here we have linearly independent as well as the columns are orthogonal, correct? So this is a matrix which is diagonalizable because the eigenvectors are linearly independent. Once the eigenvectors are linearly independent, I know the S inverse of this particular matrix will exist, correct? S inverse of this particular matrix will obviously exist. What is the condition for S inverse to exist? A matrix is invertible if and only if its rank is same as the dimension of the matrix, or if and only if all the rows of the matrix, all the columns of the matrix are linearly independent. Here we have two columns, the dimension is 2 and the rank is 2, and hence determinant will be non-zero. Determinant will be non-zero. Under that case, I can always go for inverse of the matrix. This is possible. That is why eigenvectors need to be linearly independent. For only linearly independent vectors, I can take inverse of the matrix. So that is the idea of this condition, which is this diagonalization procedure is applicable only if eigenvectors are linearly independent. Now we'll see what is going to happen with S inverse. What is S inverse? S inverse I can write as, see, the determinant of this matrix will be -1, so -2. So my diagonalization, so inverse is actually 1 by determinant, and then I need to interchange the diagonal elements. So I put -1 here and 1 here. I need to put opposite sign for the other diagonal elements. So -1 here, -1 here. Correct? This is the process of inversing. Now I take -2 inside. So I'll have the matrix given by -1 by -2. So that is 1 by 2. -1 by -2, that is 1 by 2. Again here 1 by 2. And this one will be -1 by 2. So this is the S inverse matrix. Okay. S inverse is 1 by determinant into adjoint. How to take adjoint of a 2 by 2 matrix? Interchange the diagonal elements, put negative sign, opposite sign for the other diagonal. Here interchanging, -1 becomes here, 1 becomes here, and if you put opposite sign, this becomes -1. Then I am taking -2 inside, right? So this is the S inverse matrix. Okay. Now, what if I do a multiplication of S inverse times AS? First, I'll multiply A matrix with S. A matrix with S. S is 1, 1, 1 minus 1. So I'll get the result. A times S will be, I'll get the result. What is the result? The result will be, if I multiply A times S, 3 plus 1, 4. Okay. 1 plus 3, 4. Right. 3 minus 1, that is 2. 1 minus 3, that is -2. So this will be the result when I multiply A by S. Now if I pre-multiply that with S inverse, this is the pre-multiplication part, S inverse. So I need to pre-multiply here also. A times S is this matrix. If I'm multiplying pre-multiplying by S inverse, I need to pre-multiply by the S inverse here also, correct? So I'll pre-multiply by S here also. Okay, what is going to be S inverse? S inverse is this values 1 by 2, 1 by 2, 1 by 2, and -1 by 2. So I'll write 1 by 2 here, 1 by 2 here, 1 by 2 here, and -1 by 2. What is the result? The result will be, let us see, 1 by 2 into 4 plus 1 by 2 into 4. That is nothing but 4 itself, correct? 1 by 2 into 4 is 2, 2 plus 2, 4. 1 by 2 into 2 plus 1 by 2 into -2, that is 0. 1 by 2 into 2 plus 1 by 2 into -2, 0. 1 by 2 into 4 minus 1 by 2 into 4, that is again 0. 1 by 2 into 2, that is 1, minus 1 by 2 into -2, that is again plus 1. So 1 plus 1, that is 2. And we have the result equal to, the result is an interesting matrix. This is 4 and this is 2. It's a diagonal matrix, and the diagonal elements are the, what are the diagonal elements? Diagonal elements are the eigenvalues of this matrix. Correct? Shahin, you are correct. Diagonal elements are the eigenvalues of this matrix. So this gives an important relation, that is S inverse times A times S will give you a new matrix. I am calling this new matrix by using a big lambda notation. Big lambda notation. Big lambda means a diagonal matrix where all the elements will be the diagonal elements of the matrix. So this procedure is called as diagonalization of a matrix. This procedure is called as diagonalization of a matrix. Okay. Now, if this is clear, you can easily prove one property of eigenvalues. We'll prove it. Before that, let me check whether it is possible for all other matrices. See, this idea is applicable if and only if I can take inverse of this matrix, right? Otherwise, I cannot do this calculation. That is why all matrices are not diagonalizable. For a matrix to be diagonalizable, the condition is it must have all the eigenvectors as linearly independent. Now, one property of eigenvectors, if you recollect, if all eigenvalues are distinct, naturally all eigenvectors will be linearly independent. But the converse is not true. We have seen that property in the previous class. If all eigenvalues are distinct, if all eigenvalues are distinct, right? then the matrix is obviously, then the matrix will be diagonalizable. Then the matrix is diagonalizable, right? I'm trying to write it here itself because I will give you clear picture from the slide itself. If all the eigenvalues of a matrix are distinct, then the matrix is diagonalizable. Does that mean if the eigenvalues are not distinct, they are not diagonalizable? No, because for repeated eigenvalues also, I can have linearly independent eigenvectors. That is a possibility. What we have learned is if the eigenvalues are unique, you can be sure that eigenvectors are distinct, but eigenvectors are linearly independent. If the eigenvalues are not unique, that if there is repeated eigenvalues, then there are two possibilities. Eigenvectors could be linearly independent or eigenvectors could be linearly dependent. So the converse of this statement is not true. That is, if all eigenvalues are distinct, then the matrix is definitely diagonalizable. That does not mean that if a matrix is diagonalizable, all eigenvalues are distinct. That's not correct. If a matrix is diagonalizable, eigenvalues can be either distinct or repeating. But if the eigenvalues are distinct, this statement is correct. I hope the converse and direct statements are clear to you. Is it clear? If it is clear, I can proceed to the next point. If it is clear, I can proceed to the next point. This process is called as diagonalization. I'm taking the matrix S, which are the eigenvectors. I'm taking S inverse and then multiplying the original matrix by A matrix by S and S inverse. One is post multiplication and one is post multiplication, another is pre multiplication, and the result is going to be a new matrix which will have diagonal elements only, and that diagonal elements will be the eigenvalues. Okay, so that diagonal elements will be the eigenvalues. So let us know one second, one property I can prove easily from here. So if S inverse times A times S is equal to lambda, I'll take determinant on both sides. Okay, determinant of S inverse into A into S is equal to determinant of lambda, correct? Now determinant of S inverse, determinant of ABC, product, you can take out the products, right? Determinant of S inverse into determinant of A into determinant of S, correct? I can split it like this because determinant of A, B, C is equal to determinant of A into determinant of B into determinant of C. That is a property, right? So I can always split it up. This is equal to determinant of lambda on the right side, right? So what is determinant of S inverse? We have seen that property. A to the power n, determinant will become determinant of A whole to the power n. So this is 1 by determinant of S, correct? This is 1 by determinant of S into determinant of A into determinant of S, right? I can cancel out these two terms. So determinant of A will be equal to determinant of this lambda. And this lambda is a matrix which has diagonal elements only, which are eigenvalues. So this determinant will be actually product of eigenvalues, correct? This determinant will be actually product of eigenvalues. So which means my matrix determinant will be actually equal to product of eigenvalues. Eigenvalues. So this is one property which we have listed and hence proved now. Okay. So determinant of this lambda matrix will be equal to determinant of the original matrix. All this possible only if you can diagonalize a matrix. Do you have any doubts in this particular slide? Do you have any doubts in this particular slide? Is it clear? Is it clear? Okay, we'll complete the session with a problem. I'll give the problem. It's a simple question. The maximum value of the determinant, the maximum value of the determinant among all 2 by 2 real matrices, real symmetric matrices with trace equal to 14 is? This is the question. You can try it. Yes. Sujit, Manjunath, Ishwar Iyer, Arvind Athira, Arvind Ramakrishnan, Ashwari KR, Faisa, Tasneem, Rosmi. All of you have given the correct answer. So I hope the others can actually work it out by their own. Answer is 49. Answer is 49 because when you take lambda 1 plus lambda 2 equal to 14, the maximum value of lambda 1 into lambda 2 will be equal to 49. That happens, that is similar to the area of a rectangle with the given perimeter. With a given perimeter, the maximum area happens when it is a square, correct? That you can easily prove. So sides should be same, right? Which means this, if it is, this is 7 plus 7, the product will be 49. That happens, that is a problem of actually calculus, basic calculus, which means you can maximize a function given one condition using this idea. So with that, I'll wind up the session. I'll just stop recording. You can have a doubt clearance for 10 minutes now. Okay. Any doubts which you have, you can ask now.